Okay, so today we are going to continue our discussion on detection and segmentation networks because we didn't finish last class. And then we are going to talk about recurrent neural networks. Before we start, as usual, I would like to acknowledge with respect the Lakwangan peoples on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wasanich peoples whose historical relationships with the land continue to this day. A quick note on the final project for undergraduate students. I created under assignments, so Brightspace, course tools, assignments. I created a page just for the final project, and then you can get into this page and then submit your zip file. As you remember, in your zip file, you are going to have two files, a PDF with the slides and .mp4 with the 8-minute video presentation of your final project, okay? And just a quick reminder, I discussed that on lecture 18. You have this 8-minute limit. I'm not going to be super strict if you go a little bit over, but just think about 8 minutes and 30 seconds as a hard limit, okay? And again, I'm not doing that to make your life harder. Definitely, that's not the reason why. It's just because this is a situation that you find yourself quite often in academia or even in industry, you know. So when you're doing presentations, you usually, after studying and knowing the content very well, you want to have more time to explain into detail everything you wanted to talk about, but you are typically limited to a particular time window, you know, and that's why I'm trying to enforce that just to get you used with these kinds of dynamics, okay? And I'm still giving a little bit of leeway. As I said, 30 seconds more would not be a problem, but if you go over 8 minutes and 30 seconds, I cannot allow that without deductions, because then it would be unfair with other teams that actually went through all the trouble of shrinking it down to 8 minutes, okay? So I just wanted to give a little bit of a rationale on why I'm trying to enforce 8 minutes now. Okay, so as you know, today is the deadline for assignment 4. You still have the extra 3 days with deduction, but today up until 10 p.m., if you submit your assignment 4, you will be marked without any deductions. On the 5th, we have the deadline for undergraduate students, as you know, for the video. So I'm going to create a page just like this one for the final project of ECE 536 as well. So for graduate students, okay? Probably by the end of the day, I'm going to be doing that. But since this is the first deadline, the one coming up in a couple of days, that's why I already created this page. So just keep tuned for another page just like this one, but for graduate students. Today's lecture, excuse me, is going to have the following structure. We are first going to continue our discussion on detection and instance segmentation networks. Okay, we already discussed semantic segmentation. We already discussed most of what we wanted to discuss in object detection networks, but we are going to just finish this discussion and then talk briefly about instance segmentation networks as well. Then we are going to go into today's topics, which are revolving around recurrent neural networks. We are first going to do an introduction and talk about the different types, meaning the number of inputs with respect to the number of outputs that we are going to receive. Then we are going to discuss a simple initial formulation of recurrent neural networks. We're going to call it a vanilla recurrent neural network. Then we are going to talk about the computational graph of a vanilla neural network. And then we are going to go into some applications of RNNs, in particular sequence-to-sequence, language modeling, and image captioning. Then finally, we are going to study the gradient flow in vanilla neural networks, and we are going to see that there are some fundamental drawbacks in the gradient flow, meaning when you're calculating backpropagation through these structures, and this is going to serve as motivation for long short-term memory networks, LSTM networks. You probably heard of them before. So these are special type of RNNs. All right, so continuing our discussion on object detection and instance segmentation, we finished last class talking about faster RNN, which is a 2-stage object detector. In the first stage, we are going to receive an image. We are going to pass it through a convolutional neural network. We are going to generate feature maps. On these feature maps, we are going to train our region proposal network, RPN. We already discussed what RPN is. It is going to give us ROIs, so regions of interest, where there's a high likelihood of the presence of objects. For each of these ROIs, we are going to now use the second stage, which is going to give us two outputs for each ROI, a label and also a bounding box regression, okay? But the interesting thing about this first stage, the one up until the RPN, is that when we were training the RPN, as you can see here, we have two outputs as well. We have one output which classifies each anchor as an object or not, and another one that is going to do the bounding box regression of these anchors with respect to the ground truth bounding box. So these outputs are actually quite similar to the outputs of stage number 2. The only difference, of course, is that now we are only considering two classes, which are object or not an object. And in the final stage, we are considering outputs that are given as scores for each class of the data set, but they are similar. So the question is, do we really need a second stage? And it turns out that there are a lot of methods that do not use a second stage. So they just use the first stage, but then of course with a couple of modifications. For example, you receive an image, you pass it through a CNN, you get feature maps, and then on these feature maps, you are again going to use this idea of anchors. And then for each anchor, by the way, typically folks use 9 anchors, per position in the feature map. So you have anchors of different widths and lengths, so the ratio is going to change, the overall scale is going to change as well. And now for each anchor, you want a score for each of the categories in your data set. So instead of only classifying as object or not an object, now you have C, which is the number of classes in your data set, plus background. And then times the number of anchors, times the spatial dimensions of the feature map of your particular architecture. And then of course the box transforms as well. So this is going to be used in the bounding box regression. Again, we are trying to get each of these anchors and trying to make them more similar to what would be the ground truth bounding boxes. In other words, we are classifying each anchor and we are trying to make their bounding box predictions closer to the correct ones, okay? So there are a lot of single stage object detectors like these. You probably heard about You Only Look Once, YOLO. So there's YOLO V1, V2, V3, V4. I believe V4 is the most recent one. There's also this work here, focal loss for dense object detection. This is called RetinaNet. So it's a super interesting single stage object detector as well. So those I would say are the most popular ones. In this very interesting graph from 2017, authors were comparing these different object detectors using different backbones, using a different number of region proposals. And as you can see, the choice of backbone. So what is going to be the network that is going to extract using convolutional layers the features of my image? Well, it can be a ResNet, a MobileNet, an InceptionNet, et cetera, et cetera. So this is going to be extremely important in terms of the outputs of your system, okay? As you can see, they only use two-stage detectors here. And by 2017, the state of the art was faster RCNN with Inception, 300 proposals in a certain stride, so a very particular configuration. But then, of course, throughout the years, more object detectors were proposed. By the way, the performance of single-stage object detectors in the beginning was not comparable to that of two-stage detectors, okay? So they were extremely fast, so they were considerably faster. The first YOLO was created on top of the idea that it wanted to run real time, okay, because faster was a little slower, even though it was quite fast as well. So with faster, we're talking about 0.2 seconds per image, right? So we have 5 FPS. The idea of YOLO is to get above 25, above 24, right, which would be a regular video. But in the beginning, we had this clear distinction between speed, and performance. So two-stage detectors were typically slower, but performing better when compared to single-stage detectors. Well, this difference, this gap start shortening in the last couple of years. So if you look at the state of the art, if you look at YOLO V4, for example, the performance of YOLO V4 is extremely similar to its two-stage counterparts, and it's way faster. So it really depends on what you are looking for. If you're looking for the maximum detection performance, maybe you still would go for two-stage detectors. But in my personal works, for example, I always try with faster and very interesting little tweaks that I'm going to talk about, or I tried the newest YOLO, I tried RetinaNet, you know. So nowadays, instead of looking at the architecture and saying, oh, I'm going with a two-stage detector or with a single-stage detector, the performance is really comparable. So I would just say that you go ahead and try all of the different options. And by the way, you won't often implement any of these object detectors because they are all already implemented in particular frameworks. For example, in the family of RNNs. So RNN, fast RNN, faster, mask RCNN. They are already implemented officially. For example, in the case of fast and faster RCNN by Facebook in a framework called Detectron 2. So there's Detectron 1 and then there's Detectron 2. The authors of these papers were not necessarily working at Facebook when they were first released. Now they are. So Facebook AI Research, FAIR, you know, this is the group that they are working with. And they have this repository where the newest and most efficient implementation of their works is made available. So it doesn't make a lot of sense for you to go ahead and implement them from scratch if not for academic reasons, you know. So most of them are already available, and you just get these off-the-shelf implementations and try them with a particular data sets. Okay, very good. So if we were to update this graph, we would see that nowadays mask RCNN seems to be the state of the art for object detection, and this is around 2020. So if you were to consider the object detectors from 2020, like better and efficient that, maybe this graph would change even more. So the point here is that every year the state of the art is going to move forward a little bit, in particular for object detection. So for example, some advancements in the last couple of years is that now folks are training longer because of better hardware. They are training bigger models for more time. They are using multi-scale backbones. This is a very interesting thing, so-called feature pyramid networks, FPNs. What do feature pyramid networks do? They represent your objects. So let's say that you're training to identify this bottle of water. So instead of only providing this bottle of water with a certain scale to the network, you would represent this object in different scales and then train your network with all these different scales. These are super useful. I have worked with projects where I was trying to identify very small objects with respect to the total size of the image. And these objects were just disappearing throughout my feature extraction networks, because of course the spatial dimensions start to shrink, the number of channels start to enlarge. But the point is, if your objects start really small in the original image where you annotated them, they are just going to disappear throughout the training process. So feature pyramid networks are super interesting because they are going to represent the same object in different dimensions. So it helps with this scale invariance characteristic. Better backbones, I mentioned the fact that ResNet is going to use bottleneck residual blocks, but instead of using just a single pathway, it uses multiple pathways. Therefore, it adds more nonlinearity opportunities. So folks are using ResNet quite frequently nowadays. Single stage methods have improved, as I said. So today we have single stage methods with performance comparable to their two-stage counterparts. Very big models work better. Test time augmentation pushes numbers up as well. So there are a lot of things that I won't have time to go into, but the point here is that every year the state of the art changes, either because of new models or because of new tools that can be implemented on top of models that already exist. So for example, this feature pyramid network here, it can be used with faster RCNN, it can be used with mask RCNN. So sometimes you have new architectures, sometimes you have modules that can be integrated to already existing and efficient architectures, okay? And if we are talking about state of the art, well, this is what I'm using the final projects for. So for example, in terms of object detection, we have YOLO v4, we have this paper that, again, it's not proposing a new architecture, but it's proposing a better method for the training, learning a unified sample weighting network for object detection, rethinking the bottleneck structure for efficient mobile network design. Again, just focusing on one specific part that is common to a lot of different networks, the bottleneck structure. Better, the end-to-end object detection with transformers. I'm super excited about this new line of research using transformers, which were not developed in the context of object detection, but folks, in this case from Facebook, are using transformers for object detection. So it's a completely different paradigm as what was used to this point with convolutional neural networks. There's also efficient DAT. This is an object detector from Google, which is super efficient. They have a super nice architecture as well. All that to say that I'm super excited to see what you guys are going to describe these papers with. Okay, so you're going to compare some of them for the graduate students, or you are going to create a video for undergraduate students talking about them. And I also invite you to watch the videos from your colleagues, because they are going to be talking about these kinds of papers. And that's why I asked you to look for relevant papers in recent top-tier conferences, because then we are talking about the state of the art, okay? Very nice. Now we get to the last task, computer vision, completely computer vision related task that I wanted to talk about today, which is instance segmentation. With instance segmentation, we are doing a similar thing to that of semantic segmentation networks. We are saying that each pixel belongs to a particular class, but the difference here now is that we are being able to distinguish between instances of the same class. So we can say that all these pixels are belonging to one instance of the class cow. So this is cow1. And we can say that even though there's a lot of overlap here, we can clearly divide the pixels that belong to a first instance of a class, cow1, and the second instance of the same class, cow2, okay? The approach is to perform object detection, then predict a segmentation mask for each object. So the reason why I'm only talking about instance segmentation now is because it is going to be built on top of the structure for object detection, as you're going to see. So we are very familiar with this architecture by this point. This is faster RCNN. The only thing we need to do in order to do instance segmentation is to add an extra branch, is to add an extra output on the stage 2 of faster RCNN. This is now called mask RCNN, okay? So it's exactly the same thing we were doing, but now once we receive an ROI, we are going to do the label, we are going to assign a label to it. We know how to do that. We are going to do bounding box regression. We also know how to do that. Now we are going to provide an extra output, which is the mask prediction. The mask prediction is going to tell you for each channel, what is the probability that a pixel belongs to a class. Does that sound familiar? Well, this is exactly the same thing that we were working with semantic segmentation networks, okay? So let's see how the structure of mask RCNN looks like. First, pass the input image through the backbone network to extract feature maps. Exactly the same thing as faster. Region proposal networks use such maps to determine ROIs. Again, same thing as faster. Each ROI will be used as input of a semantic segmentation task, aside from the regular faster RCNN usage, okay? So once we get to the output of the RPN, we know that one part of this output is going to go to the, say, regular output of the network. It is going to give us a label, and it's going to give us a bounding box regression. Very good. But now we are creating a new branch, a new output, which is going to implement a semantic segmentation network. So that's exactly the same thing that we were discussing last class. We are using fully convolutional networks. We are using a lot of convolutional layers. And then in the end, we'll have the number of channels for each of these ROIs being equals as the number of classes that we have. Again, we use, I don't know, softmax, or we can just look at the highest score for each of these channels. This is going to be the prediction for each pixel inside of an ROI. So it's super interesting because since we are using the structure of faster RCNN, each instance segmentation detection is already going to be accompanied by a bounding box encompassing it, a score. These come from the traditional output of faster RCNN, plus the specification on a pixel level of what is composing this said detection, okay? How do the segmentation targets for each class look like, considering a given ROI for the RPN? So you might be asking yourself how to annotate this data, for example, to be trained with mask RCNN. Well, the idea here is that we are going to specify for a given image which pixels belong to each particular class. So if we are considering this bounding box here, we would manually annotate these pixels as being an instance of the class chair. And then if we have a bounding box like this one, well, in this bounding box, inside of it, we have pixels from different classes, right? If we were annotating for the class bed or sofa, for example, we would have to manually, and there are a lot of different tools that you can use to do that. There are MATLAB tools. There's a tool called Label Me, which I recommend using. It's very good. But at any rate, you can specify what are the pixels belonging to each class, and then you can train your mask-RCNN using these annotations, okay? These are some results from the original paper of mask-RCNN. As you can see, it can clearly distinguish between two motorcycles. So it's telling you what are the pixels of the motorcycle. It's telling you what is the bounding box encompassing it. It's also distinguishing between two instances of the same class that are overlapping each other. As you can see here, a lot of instances of the class person as well. And here the same thing. So very interesting results with mask-RCNN. There's a small thing that I didn't talk about. This is actually the terminology used, you know, even though it doesn't sound super professional. When you're working with huge data sets like COCO, which is a data set of natural images annotated on a pixel level created by Microsoft, it's a very challenging one. So there's a COCO challenge as well, similarly to the ImageNet challenge. They distinguish data sets of things and data sets of stuff. Okay, so things are those that you can count. For example, one instance of a cow, one instance of a zebra, there's two people on an image, etc. Okay, so instance segmentation deals with things. It does not deal with stuff. Okay, what would be stuff? Well, those that are not countable. So for example, how many grasses do I have in an image? How many skies do I have in an image? It doesn't make a lot of sense to count those, so those are considered to be stuff. Again, instance segmentation typically deals with things, but you can imagine situations where you would want to identify both things and stuff. Those are the panoptic segmentation networks. So these networks are doing an pixel level detection of different instances of the same class. These are things, as well as finding stuff. So they are kind of putting together the output of instance segmentation and semantic segmentation networks. And as you can see, if you are working, for example, with autonomous driving systems, you would be interested in distinguishing between different instances of cars, but at the same time, you would be super interested in knowing what are the boundaries of the road ahead, okay? So these are just some examples of panoptic segmentation networks, and we won't go into the details of the architecture. We also have the identification of human key points. So the joints, for example, that you expect from a human in order to determine exactly what is its pose, okay? In this case, it was interesting because in the original paper of mask-RCNN, they show that it's super easy to do this kind of task, human key points identification, by only adding a new output to the end of your mask-RCNN. So we were talking about the mask prediction. That was the difference between FASTER and mask-RCNN. Now we are going to add key point prediction as well. So in this very same paper, it's a great paper, right? So in the mask-RCNN paper, they show examples of pose estimation by identifying the human key points, okay? Using the structure of mask-RCNN. Perfect. And then on the next lecture, that would be the end of Monday's lecture, we were going to talk about recurrent neural networks, which we are going to do right now. So far, we've been talking about feed-forward neural networks. In particular, we took one task, image classification, because it's a problem that encapsulates a number of important topics for machine learning and deep learning. However, deep neural networks can be used to solve a number of other problems as well. As you know, they can be used, for example, with text, with sequences more generically. And this is what we are going to talk about in this class. So up to this point, we were working with one-to-one networks. So networks that, given one input, provide one output, okay? Sorry, this is image classification, because object detection, actually we have one input and multiple output. But considering image classification, you provide an image and you are then left with a label. Granted, you have a lot of different scores for the different classes, but remember, the prediction is a single label, maybe the highest one, maybe the one with the highest probability. Today, we are going to talk about how to process sequences. And there's a lot of different types of data that work with sequences, right? So if you have the measurements of a certain instrument, if you have frames of a video, these are a sequence. If you have words, these are a sequence of characters. If you have text, which is a sequence of words. So there's a lot of different types of data that you can interpret as sequences. Spoiler alert, you can also interpret images as sequences, single images, as we are going to see. But in terms of the types of recurrent neural networks, which are these networks that work with sequences, we have one-to-many. For example, when you provide an image and the network is going to output a caption to this image. And by the way, this caption can have a different length. You don't know exactly, it depends on the contents of the image. Once I was preparing this class, I wanted to show you some examples of how hot this research topic is. So for image captioning alone, there's a lot of what you can consider state-of-the-art works, and this is a paper from 2019, so it's not even that new. So this is a survey paper that compares a lot of different techniques just for image captioning. Then you have this other family of recurrent neural networks, which are going to receive many inputs, for example, a sequence of frames, and they are going to provide a single output. For example, a classification of all these frames as an action sequence, as I don't know, a sport sequence, something like this, okay? These are some state-of-the-art works that I also researched a couple of weeks ago. So these are very, very recent, very nice. There's many-to-many as well. Say that you have a sequence representing a sentence in a certain language, say English, and you want to provide the translation of this sentence in another language, say French. You don't know exactly what is going to be the length of the output sequence. You know the length of the input sequence, but say that a 3-word sentence in English is translated to a 4-sentence word in French, for example. So many, a number of different elements, too many, another number of different elements in the input versus the output, okay? And again, I was doing a bit of research to show you what the state of the art is. And then this is a paper that was published on Nature. And as you can see, a deep learning system reaches news translation quality comparable to human professionals. So nowadays, these machine translation systems are as good or sometimes even better than the human professional counterparts. And then finally, you also have many-to-many for the same number of elements in the sequences. So for example, if you're doing the classification of each frame of a video, that would be a sequence with length X in the input and a sequence with length X in the output as well. So there's all flavors. It depends really on the task that you're working with. The length of the sequence in these examples might not be previously known, as I said, so you don't know necessarily what is the total size of a video. Since you are providing one output per frame, you can just keep receiving input indefinitely, because for each frame, you would provide one output, okay? So when you're talking about sequences, they can come in all different shapes and sizes. An interesting motivation on why we would want to use RNNs even for non-sequential data are these examples here. So can we use sequential processing for non-sequential data? In this work from 2015 called Draw, what authors were doing was taking small glimpses of the image. So small parts of an image, they were only provided with a single image. And then they were creating a sequence by reading this image one part at a time. And then if they were reading, following the same strategy, different samples of this data set, in this case, the MNIST data set that you are already very familiar with, they were actually creating sequences for each of these characters, okay? And then based on these sequences, they were using a many-to-one. So they were receiving a sequence, in other words, the different parts of an image, and they were classifying this sequence with a single label. For example, this is digit 0, this is digit 1, up until digit 9. And in the same work, Draw, they are doing the other way around as well. We are going to study language models where you are going to provide a part of a sequence And since the system was trained in a certain dictionary, in a certain vocabulary, it is going to, given one sample, predict what is going to be the next sample. You can think of the autocomplete systems that you are used to use. For example, you start writing a word, and then Google tries to complete this word or complete a whole sentence. So these are language models because they are learning on a training set where they are looking at the structure of either words, composition of characters, or sentences, compositions of words. So if you use the same strategy here, you can think of these glimpses of the image as sequences, and provided with a couple of pieces of the sequence, the system can be trained to find what are the other parts of this sequence. In other words, generating images one piece of the sequence at a time. Super interesting, right? Okay, so hopefully that was enough motivation. Let's now dive deeper into the structure of vanilla RNNs. So we are saying that these are vanilla RNNs because this is the structure that most RNNs have, but without the bells and whistles. As we know, we start with something simple, and then we talk about the drawbacks of these simple approaches, and then start correcting them. So this is going to be the simple version of recurrent neural networks. We are going to call them vanilla recurrent neural networks. The key idea here is that RNNs have an internal state that is updated as the sequence is processed. Okay, so we have an input, we have an internal state, and then based on this internal state, we can provide an output, depending, of course, on the flavor that you chose, right? So you can have a number of internal states and provide a single output, or for each internal state, you provide one output. It really depends. Okay, at each time step t, the RNN receives an input X, updates the internal hidden states, which in turn changes the output for this particular time step, if this is how your network is designed. We need a recurrence formula to model this relationship. So how can we change this internal state? We know that we want to capture the temporal relationships between the elements of the sequence. So for sure, in order to find the value of a certain current internal state, we need to take into consideration the last internal state plus the current input, okay? So this is exactly what happens. The new state is given by a certain formula that is going to relate the old state, so the state that came from the last time step, t-1, plus the current input of this particular recurrent neural network, okay? A very common formulation of this relationship is given by an activation function, 10h, and now we have the multiplication of the last hidden state by a certain weight matrix, this one, plus another weight matrix, a second weight matrix, okay, multiplied by the current input, and then you put these two together. You can think of cases where the dimensions of the hidden states are different from the dimensions of the input of your sequence. So you need two different weight matrices that are going to make these dimensions match. So based on the dimensions of the last hidden state and the current input, you would have to use weight matrix with different dimensions so that the results can be summed together afterwards. Very good. And then, of course, once you have a hidden state, you can either pass it on to calculate the other hidden states in the future, or you can calculate the output right away, as we are going to see an example in the computational graph. When you have to calculate the output, you are going to get the value of a hidden state and multiply it by yet another weight matrix, okay? So as you can see, we have a lot of weight matrix this time, differently from just a single weight matrix per layer that we had on neural networks. So let's look at the computational graph and some different flavors for RNNs, many-to-many, one-to-many, etc. We start with initial hidden state, either set all to 0 or learn it, so that's an interesting point. There's a lot of research on what should be the initial hidden state, because of course, as you noticed by now, each hidden state is going to influence in the value of all the other hidden states in the network, because in order to calculate the following one, you will consider the value of the current one, and so on and so forth, okay? So the values of all hidden states are going to be extremely important. What about the value of the first one, where you didn't do any calculation yet? Well, typically it is set to 0, but there are a lot of systems that try to learn what is the ideal initial value as well. At any rate, we are going to use a recurrence formula that considers the previous hidden state. In the first step, we don't have one, so we say that it's H0, which, as I said, typically starts with 0, and the current input. Very good. Given those two, we can calculate the current hidden state at time step 1. And then for time step 2, we are going to consider the hidden state from time step 1, this one right here, plus the input at the current time step 2. So this is going to be H2, and then you can keep going. Again, you have a lot of hidden states up until the end of your input sequence. You get up until a final HT. And then an important thing to note is that we are going to use the same weight matrices. These two weight matrices that I was talking about, they are always going to be the same for all these different hidden states. That makes total sense. Why? Because you don't know what is the length of your input sequence. So if you don't know what is the length of the input sequence, how would you know how many different pairs of weight matrix you would be required to learn? There's no way to know. So instead, we use the same set of weight matrices to find the hidden states. Let me go back here. Another interesting note is that we now are using a copy gate, right? Since we are getting these same weight matrices and using in different parts of the network, this is equivalent as using a copy gate. And during backpropagation, the gradient of a copy gate is going to be the sum of upstream gradients into the downstream gradients. So this is a nice exercise to always do. Whenever you're designing a network, thinking about how the gradient flow is going to be when you're doing backpropagation. In this particular instance, this is not going to be a problem. We just have to sum the upstream gradients coming from all these different parts of the network that use the same pair of weight matrices. Very good. So if we were talking about a many-to-many network, for example, a network for per frame video classification, each of these hidden states would be again multiplied by yet another weight matrix to find a certain output. So for each frame, we could say, for example, okay, this frame contains movement, this one does not. You can think of other tasks as well. The hidden states are subject to a linear transform of this weight matrix, generating the outputs. And then, of course, once you have the outputs, you can compare them with the correct outputs. These come, of course, from an annotated data set. So let's say that you annotate a data set saying that from frames 10 up until 100, there's movement in a video, and from 101 up until 200, there's no movement. So then for each classification, you could do this comparison using a loss function between the prediction for each frame and the correct label for each frame. And given the prediction and the correct annotation, you could calculate the loss. And similarly to what we were doing with image classification, you put all the losses together. This is your final loss for the system. And then you start the backpropagation through this final single valued loss, as we know how to do. If you were working with video classification, for example, you would not calculate the output at each hidden state. You would just calculate all hidden states throughout the network, given, of course, by the length of your input sequence. And then the last hidden state, which again carries the relationship between all of these partial hidden states. So it has got memory from all the different parts of the sequence. Well, this hidden state would be used to calculate the final output for your sequence. So classifying the whole video, for example. Image captioning is a super interesting one, because image captioning, you are going to provide an image as a single input. We'll see exactly how this input looks like. And then you would calculate a number of different outputs. Each output here would be one word of your caption. It will make more sense when we talk about language models, but as of right now, just think about this single input as being an image, and each of these outputs as being a word. All right, so another interesting task is called sequence to sequence, the one that I was describing before as machine translation. A sentence of X words in English might be translated to a sequence of Y words in French, and X might be different from Y, of course. Therefore, these RNNs must be able to work with sequences of different lengths. So how can you have a sequence of a certain length in the input and a sequence with an arbitrary length in the output? Well, we are going to use a many-to-one network as sort of an encoding network, and another RNN of one-to-many as a decoding network, okay? So it's a very interesting idea. What we are going to do is to use, as I said, this many-to-one network as a first step to encode the input. For example, this is the sentence with English words, and then you put them all together. The contents of the sentence are going to be encompassed by this single hidden state here. And then on the other side of the network, you use another network, a one-to-many, that is going to consider this hidden state, therefore all the input sentence, and it's going to provide a number of outputs, depending, of course, on how many words you need to translate this input English sentence. So with this architecture, you can have an arbitrary length for the input sequence. It doesn't matter. It's always going to generate a single hidden state. And then with this hidden state, you can do whatever you want. For example, providing it to a one-to-many RNN, and this one-to-many RNN is going to create a number of words for the output, depending on the language that you want to translate it to. The weight matrices used in the two steps are different. That goes without saying, right? So these weight matrices are used just for the encoding part. These weight matrices are used for the decoding part. So we are doing actually different things. Very nice. So now let's look at an extremely important task called language modeling. And we are going to talk about the dynamics of training right now. And then we are going to look at testing. So for language modeling, the goal is to process theoretically infinite stream of input data. It is not going to be infinite, of course, but it could be infinite with this architecture. And at each time step, we are going to predict what is going to be the following character, okay? So in this example, we are talking about characters. So we are talking about, oh, I provide an H, the network predicts an E, and then predicts an L, et cetera, et cetera. You can think as this prediction instead of characters as being the prediction of words, okay? And we are going to get to that when we discuss image captioning. But as of right now, we are building words. And by the way, one character can be space, okay? So if you build a word and then you predict a space, you can build another words. Therefore, you can build sentences, but one character at a time instead of one word at a time, okay? Very good. So what we first need to do is to define a vocabulary, sometimes called a dictionary as well. And each element of this vocabulary is called a token. So in this case, we have only 4 tokens. We want to illustrate with the word hello. So we will repeat the L, but just 4 individual tokens. The way that we are going to represent each token is what we call a one-hot vector, okay? So one-hot vectors are extremely simple. For each token in your vocabulary, you have 1 in one position and 0 in all the other positions. It's not binary, as you can see. So if you have 4 different tokens in your vocabulary, you have 4 dimensions in the one hot vector representation of them. Okay, so H would be represented as 1 and all zeros, E as 0, 1 and all zeros, etc., etc. You might be thinking, oh, there are way better ways to represent these vectors, and this is actually the case. So I have some extra slides on layers called embedding layers. They're going to represent, these tokens in a different way. But as of right now, let's just consider one hot vectors, okay? That's very good. So during training, what we're going to do is provided one token, we are going to use the weight matrices that we were talking about to find the values of the hidden state, this hidden layer here. And as you know, the values of one hidden layer are going to influence in the values of the next hidden layer, as well as the input for this next time step. That's very good. In the case of this training here, we want to predict for each hidden state what is going to be the output, what the output represents, the next character, okay? So given H, we are going to calculate this hidden state. Given this hidden state, we are going to calculate this output layer. This output layer is going to tell us what is the likelihood for each of the tokens in our vocabulary. And as you can see, the highest output here was associated to the token of E. So that's why the network predicted an E, and the target character, because we are still doing training, so we have the ground truth, was also E, okay? And then we can use a loss function to see how far away we were from the correct one. And then in the second character, we provide an E, and the network will hopefully predict an L. As you can see, that was not the case here. It predicted, what is this, an O, okay? So it was wrong in this particular step. Well, we are still doing training. So we look at the prediction, we look at the ground truth, we calculate the loss, and then we do back propagation through that. That's very good. So let me keep going here. During testing, what's going to happen is that, let's say we provide a single character, okay? So we provide H, and then given H, our output was this one here. As you can see, the highest score was associated to the second position in the one hot vector representation. 0, 1, 0, 0 represents an E. So the network is telling us that the next character is likely going to be an E. That's very good. So let's use this prediction as the input for the next time step. So E is going to be the input of the next time step. If we look at the prediction of the network, it now predicted hopefully an L, and then an L again, and then finally an O. Okay, so in the language modeling, we are providing tokens. In this case, these tokens represent characters, and we are waiting for the next tokens, okay? That's very good. So one thing that we should discuss is the fact that, look, if your inputs are theoretically infinite in length, there's no way for you to do a forward pass because you don't know how long this is going to take, nor how big this input is going to be in order to start doing the back propagation. So when working with RNNs, there's this idea of back propagation through time. The idea is that you have an arbitrarily big sequence as an input, but you are only going to consider chunks of it at a time, okay? So let's say that you receive, how many do I have here? 7 pieces of my sequence. I do a forward pass through these sequences. I calculate the loss for each of these time steps, and then I do back propagation just on the parameters of this first chunk of my network. And then when I look at the second chunk, the following 7 pieces of the sequence, what is going to be connecting the first chunk to the second one? Well, the hidden state, the last hidden state of the first chunk. So they are connected naturally, but I already went through a pass of forward and backward, a forward pass and a backward pass with back propagation in the first chunk. By doing that, I'm partially training my network throughout these arbitrarily long sequences, okay? And this is what it's called back propagation through time. In particular, truncated back propagation through time, okay? Because we're working with chunks of the input. And now some interesting examples. Folks used vanilla RNN to train on the sonnets by William Shakespeare, all 154 sonnets. And as you might know, they all have 14 lines. So it's not a gigantic data set, but they train these sonnets to create new sentences, one character at a time, okay? So let's just look generically at the beginning of the training. So after training for a couple of epochs, you provide a character and maybe you are left with this gibberish sentence here. As you can see, it was not able to create words that made sense, let alone, so the grammar was wrong, the syntax was wrong, so it really didn't make a lot of sense. But for the same data set, if you train a little bit more, now they start to look as correct and valid words. You have here, you have what else? In, so you have a couple of words that are already starting to make sense. And if you train a little bit more with the same data set, now you have a lot of words that make sense. You have fall, where, to, it, me, that, etc. And if you train even more, then things start making a lot of sense. Why do what that day? Well, maybe that's not a regular way to speak, but at least you're using valid words. And then after training for a lot of time, it was interesting to see that vanilla RNN was actually creating dialogues for particular characters of that appear in these sonnets. They were creating sentences that now make sense. And of course, this is just vanilla RNN with a relatively small data set. But if you look at the state of the art, which I believe to be GPT-3, I was looking at some examples of how GPT-3 is powerful. And there's this super interesting news piece from The Guardian that reads, a robot wrote this entire article. Are you scared yet, humans? So it's a full article written by GPT-3, which of course is a language model. But this language model was trained in a completely gigantic data set, okay? So all kinds of sentences, all kinds of topics. This data set was not focused in the sonnets by William Shakespeare, for example. It was actually grabbing text from all over the internet. And then if you provide a couple of key words, so let's say you provide Trump, politics, maybe scandal, it will create a whole news piece based on these keywords and all of the language modeling that was done beforehand. So it's extremely interesting, and I recommend that you read this article here, which is a little scary, if I'm being honest. And then using vanilla RNN, folks also trained a code generator on top of the original Linux code. And as you can see, it was able to create structures like ifs, fors. In the beginning of files, it was providing copyright notices and everything. So it's very, very interesting. All right. That's very good. I think I'll have time to discuss everything. Now, I would like to talk about image captioning, because image captioning is a little different, right? I was talking about sequences. Once we receive sequences, we know kind of what to do now. But what about images? Images are not sequences, right? Well, not exactly, but we can easily interpret them as being that. The idea is that in this one-to-many problem, one, because we are providing one image, many because we are providing as an output many words as a caption for a certain image with a different length. That's important. Input an image to a CNN, which we are very familiar with, that will extract its features as a flattened vector. So this vector of flattened features is going to be considered as our sequence now. Input this vector to an RNN that will output words one at a time, and they are together going to compose a caption. So we have a convolutional neural network to turn our image into a vector of features, a flattened vector of features. And then this vector of features is going to be used as a sequence, as the input of a recurrent neural network, which is going to use the language modeling to predict what are going to be the next tokens based on this initial sequence that you provided. Very interesting idea, right? So let's see how it would actually work, because just by looking at this diagram, you might still have a couple of questions. So we would typically use CNN. We discussed transfer learning, I believe, 2 classes ago. So let's say that we were using CNN trained on ImageNet. As you know, ImageNet has got 1,000 different classes. So instead of that, we are just going to grab a flattened version of the features coming from an image. So we are chopping the last 2 layers of a particular CNN. I do believe that this is AlexNet. And then we are left with this sequence representing the image. This is what we want for the RNN, right? All right, so this is the CNN part. Let's now just focus on the RNN part, and then we are going to connect them together. For the RNN part, we are doing language modeling. But now we are not working with characters anymore. You could work with characters, I believe, but when doing image captioning, typically the tokens are full words, okay? So what you're going to do is to have 2 special tokens, this one, which is the start token, and the last one called the end token. The end token is going to be the one present when your caption ended. Because how big is going to be your caption? Well, this is given by when the end token appears, okay? Differently from some other language models, in image captioning, we want to define a clear start and end to a sequence, okay? Thus, we first pass a start token. So we know that we are starting right now. After the end, we can maybe receive another image. We would pass the start token once again. It's just a flag, so the network knows that it is going to receive the sequence representing an image, and that it is going to start outputting the words of a caption. Before, we had a recurrence formula for the hidden states that was given by an activation function and a combination of the last hidden state plus a multiplication between a weight matrix and a particular input plus a bias. Very good. So this is what we've been discussing with the vanilla RCNN. For image caption systems, in the first hidden state, we are going to add an additional term. What is going to be this term? Well, it is going to be a multiplication between a weight matrix and the vector representing your image, okay? So it's interesting to see that once you keep going through this network, this vector representing your image is not going to be used in the calculation of the other hidden states as well. When you're reading, for example, this paper here, let me go back. Okay, so this paper here, deep visual semantic alignment for generating image description. So the one where this image came from. The authors say that, look, we've tried using this sequence representing the image in the calculation of all hidden states. It works better if you only use it in the calculation of the first hidden state, because remember, the content of this first hidden state is going to be used in the calculation of all the other hidden states as well. So in the end, they are only using the sequence representing the image in the calculation of the first hidden state. Very good. So the first hidden state is going to be calculated as a combination of the initial hidden state, the sequence representing the image, the input, plus the bias. Again, the input for this first time step is going to be the token start. Very good. So you provide all that, you calculate a hidden state, and then you calculate the first output, which is going to be a word. And then this word is going to be the input for the next time step. So in the next time step, we are again going to calculate what is going to be the hidden state. As you can see, the calculation of this hidden state in time step 1 uses the value of the hidden state, the initial hidden state. In other words, it is using implicitly the content of this image that you provided, not a problem there. And then at the output of it, you have another word that's going to be the second word of our caption. And then you keep going, keep going, keep going, up until the point where the network wants the caption to end. When is that going to happen? When the network predicts the end token of your vocabulary, okay? So whenever the network predicts that the next word is going to be the end token, that means that the caption is over. Very nice. So let's see some examples. These were using NeuroTalk, in particular NeuroTalk version 2, okay? So you provide these images, and these are the captions that were generated. Super interesting captions. As you can see here, for this image, a cat sitting on a suitcase on the floor. That's perfect. A dog is running in the grass with a frisbee. Wow. 2 giraffes standing in a grassy field. As you can see, we have 9 words here. We have 7 words here. So the length of the caption can be different. Again, we start with the start token and the vector representation of our image. That's the first time step, and then we keep going through a number of time steps up until we get to the end token of our dictionary, the prediction of the end token. The prediction of the end token, which is the end of the caption. Very good. So these are successful instances of these systems, but there are also failure cases. For example, in this one, a woman is holding a cat in her hand. Maybe the network was confused by the texture of this woman's coat. A woman is standing on a beach holding a surfboard. That's an interesting one. So maybe in this data set, there were a lot of images with water and people holding surfboards. So whenever the network receives or identifies, right, water, it thinks that there's someone there holding a surfboard. So there's a lot of bias with respect to the data that you provided during training, of course. And this is an extremely interesting and hard example, a man in a baseball uniform throwing a ball. So as humans, we know that the physics of this ball throwing are that the ball is coming towards the player, not the other way around. But just by looking at an image, it's hard to model that for the network automatically, right? So this is a very interesting example. All right, so the last topic that I wanted to discuss today refers to the gradient flow, and in particular, the problems with the gradient flow when working with vanilla RNNs, and then how to solve them. Very good. So this is the diagram representing the vanilla RNN that we've been discussing so far. And if we think about what happens during backpropagation, you see that when we do backpropagation from the current hidden state to the previous hidden state, we are going to go through a nonlinearity, the 10H nonlinearity. And you remember what happens with 10H, right? So in 10H, you have values being squashed between 1 and -1. Regardless of the input, the values are going to be 1 and -1. Depending on the values that you're providing to 10H, maybe completely different values would have extremely similar nonlinearity outputs. So if you're providing big values, for example, they are always going to be turned to 1. If you're providing super small values, they are always going to be turned to -1. And if this is the case, the input is not influencing in the output. Therefore, the local gradient is 0. And if the local gradient is 0, the downstream gradient, which is the multiplication of the local and the upstream gradient, is also going to be 0. In other words, there's no learning. Whenever you're doing backpropagation through nonlinearities, you run into this problem, depending, of course, on the characteristics of the nonlinearity that you're using. So that's problematic. Another problem is that we are going through a matrix multiplication. And if you remember from lecture 16, whenever you have these cases where you are multiplying the input by a weight matrix, you would go through the process of calculating the Jacobian to find the local gradients and then multiplying this Jacobian by the upstream gradient. So it's a lot of work, but we also mentioned that you can do implicit calculations. You can avoid the calculation of the Jacobian altogether. And at the end of lecture 16, we came to the conclusion that you only need to multiply the transpose of the weight matrix by the upstream gradient in order to find the downstream gradient. So this is what you would have to do here as well. You would have to multiply the upstream gradient coming from HT by the transpose of this weight matrix. So we have basically two problems with the vanilla RNN. We are going through a nonlinearity, which I just explained is problematic, and you are also multiplying something by the transpose of this matrix. If this matrix has got high values, if it has got values that are significantly bigger than 1 or significantly smaller than 1, what is going to happen is that since you're using the same weight matrix and multiplying its transpose over and over and over and over by gradients coming down the network, these values are going to explode in what we call exploding gradients. Or if they're too small, so say if you use values as small as 1.2, for example, you would multiply something by 1.2, and then this output 1.2 by 1.2 again, and then 1.44, something like this. And then you would multiply this by 1.2 again. So you would grow exponentially and your gradients could quickly explode. Same thing happens in the other way around, of course, for vanishing gradients. You could easily go to 0. And remember, whenever our gradients explode or go to 0, the learning is not possible anymore. To solve this first problem, the problem of exploding gradients, sometimes people use a trick called gradient clipping, where you calculate the norm of the gradient, and if it's bigger than a certain threshold, you are going to divide it by the gradient norm. So in other words, you are just clipping the gradient, you are changing it in a way that it doesn't explode. So this is not ideal, of course, because you are messing with the characteristics of the optimization, which would naturally occur, but this is something that folks sometimes do. And you can also work in the other way around. So how to prevent vanishing gradients? Well, you could look at the size of the gradients and maybe add a little constant, but again, you would change the fundamental nature of these optimization schemes. So for vanishing gradients, what folks typically do is to look for another architecture. In this case, another RNN architecture. And it is in this context that we are going to discuss LSTMs, long short-term memory networks. We are going to look at its structure, and then we are going to look at how the gradients flow through it, because it's going to make more sense. But this is how LSTMs look like. Now, in each time step, instead of having a single hidden state, we are going to have one hidden state in what we call the cell state, okay? When we do the multiplication, the recurrence formula, right? So when we do the multiplication of the input by a weight matrix and sum with the multiplication of the last hidden state in a weight matrix, that was going to be the next hidden state for a vanilla RNN, right? For LSTMs, we are going to break this output down into 4 gates, okay? So we have the input gate, the forget gate, the output gate, and there's the G gate, let's just call it gate, okay? So these gates are going to be used to calculate the cell state, CT in this case. So as you can see, to calculate CT, you use the F, Y, and G gates. And then once you have the cell state, you're going to use this cell state to calculate the hidden state. So we are adding this extra step here. So to calculate the hidden state, you're going to do an element-wise multiplication between the output gate and the 10H of the cell state, okay? So this is a nice illustration of what I just said. You have a weight matrix. As I said, you are going to use probably weight matrices of different sizes, but in this illustration, you have one set of weight matrices, you have one hidden state coming from the last time step, and you also have the input for this particular time step, okay? You do the multiplication of them, and then you have a result here. For vanilla RNN, that would represent the hidden state for the next time step. For LSTMs, you are going to break this result down into 4 equally sized gates. So as we said, we have the input gate, the forget gate, the output gate, and the gate. So because of why each of these gates were created, they are going to be squashed into different ranges as well. So the input, forget, and the output gate are all gates that are going to tell you how much each element coming from other state is going to be reproduced in the current state. So it makes sense that we use a sigmoid activation function. We are then squashing them between 0 and 1, but the gate is going to tell you how much to change the current hidden state based on the contents of your input. So this one changes from -1 to 1, okay? Very good. So let's look at each step of the calculation of the cell state. In the first step, we are going to do an element-wise multiplication between the forget gate and the last cell state. So the cell state of the last time step. And then we are going to sum this with a multiplication of the input gate and the gate, okay? Very good. Once we calculate the cell state for a particular time step, we are ready to calculate the hidden state for this same step. So the hidden state is going to be given by an activation function on top of the current cell state and the element-wise multiplication with the output gate. As you know, the output gate ranges from 0 to 1, so we are going to tell you how much from the output of this activation function is going to be passed through into the calculation of the next cell state, of the next hidden state, etc., okay? It is very common when studying LSTMs to look at a diagram like this, and it is going to help us in looking at the gradient flow now for LSTMs. This diagram tells us exactly the same thing as the formulas that we were studying. For instance, the calculation of the current cell state is given by the element-wise multiplication of the forget gate and the last cell state. As we can see here, last cell state, element-wise multiplication with the forget gate, okay? All right, so finally we got to the gradient flow of LSTMs. When you are doing backpropagation, when you are calculating the gradients for each element of each cell of LSTM, you are going to come this way. And as you know, we are also going to do the backpropagation through these different branches, through these different paths as well. But let's just concentrate on this top path here. What are we going through in this top path? Well, first we have the sum node here, and you recall that when backpropagating through a sum node, one simply distributes the upstream gradient into the downstream gradients, okay? So I have an upstream gradient coming from CT. I am just going to copy and paste this upstream gradient into the downstream gradients of the different paths coming out of the sum node. So that's extremely easy to do, not a problem at all. And then we are going to backpropagate through an element-wise multiplication. We are not going through nonlinearities. We are not going through weight matrices. So what happens is that this top path is going to represent an uninterrupted gradient flow. In other words, the gradients coming from right there at the end of your network, or right there at the end of the trunk that you're training at a time, as we discussed, is going to have an uninterrupted path to go from the end of your network, or the end of this part of your network, up until the beginning of your network, or this part of your network. And this is exactly the same idea that was used with ResNet, if you remember. So for ResNet, we had residual blocks, which were connecting the input to the output. And during backpropagation, we were copying this upstream gradient to the downstream gradient, plus whatever was happening inside of the residual blocks. So even if we have exploding or vanishing gradients inside of the residual block, this upstream gradient being copied to the downstream gradient would still happen. So it would create an uninterrupted gradient flow there as well. The idea here is quite similar. Of course, as I mentioned, we still have to backpropagate through nonlinearities in the weight matrix when we go through this path here, but the hope is that this uninterrupted gradient path is going to preserve information and allow for an efficient training, okay? All right, so if this is the first time that you're hearing about LSTMs, that might seem a little overwhelming. I acknowledge that. So I guess if you have any questions, you can ask me now, or you can go back to the recording of this lecture. But the idea here is just to understand that the gradient flow for LSTMs is a little easier than for vanilla RNNs. What happens with vanilla RNNs is that if you're working with small networks, they typically work quite well. But if you're working with longer sentences, the memory of the vanilla RNNs is going to become problematic. Why? Because you have vanishing gradients, you have exploding gradients. So that's why LSTMs were proposed. LSTMs are not the state of the art. There are also GRU RNNs networks that we won't have time to discuss, but they are similar to LSTMs. They're like cousins to LSTMs, and they also have very nice gradient flows. So as long as you understand why LSTMs are there and what are their differences to vanilla RNNs, I think you should be fine, okay? And you listen to it once, it might seem a little confusing. When you listen to it again, it will be way clearer, okay? So if you look at this class again, I'm sure that that is going to be easier to understand. Very good. So up until this point, we've been talking about single layer RNNs. RNNs that were calculating a single hidden state for each time step. But you can think of RNNs that use each hidden layer as the input for a second RNN. So they are going to create multiple layers. In this 2-layer RNN, for example, we are calculating the hidden states and then using these hidden states as inputs to another RNN on top of this one, effectively creating another layer. And then you can do 3 layers, 4 layers, etc. You typically don't go as deep as we do in convolutional neural networks, so you won't see 152 layers RNNs as we have with ResNets, for example, but up until 5 layers, I think it's quite common to see, okay? And that is it for today. Very good. I didn't think that I was going to be able to discuss everything, but that's super nice, because then in the next lecture, we are going to talk about generative models. I'm hoping that I'll be able to talk about all the bases and then discuss generative adversarial networks. Unfortunately, it's going to be a little hush-hush, as this class was, but I guess that at least being exposed to the ideas of generative adversarial networks will be useful for you, okay? And then, of course, in your own research, you can go into more details about that. Do we have any questions about today's lecture, or maybe the final project, anything like that? All right, so I have a question here. I have a question regarding assignment 4, block 2.4, 2.5, which is regarding testing and training our CNN. My question is, if we do not use your variables or follow step-by-step the direction you wrote in the comment, okay, is there a problem that we just follow the purpose of the block? Because I was successful to train and test the convolutional model, but I have a problem in using your variable or direction step-by-step in this section. I just want to ask whether I will lose points or not. Okay, so it shouldn't be a problem, Elmira, if you are following, in the case of these particular blocks, if you're following the architecture that I provided, okay? So let me see. Okay, so just as an example, in the structure that I suggested in the assignment, you are first declaring the convolutional layers and the max pooling layers. And then you are putting them together with the nonlinearities and the fully connected layers in the forward function, right? So you could do all of them in the same function. That's another way to implement. So as long as you are implementing the architectures that I'm specifying, you should be fine, okay? The problem with going too custom with your solution is that if you are not following the architecture that I'm talking about, and that's the reason why I provide the template, right? Because if you go through the template, you are necessarily following this architecture. So you can go other ways, but then if you don't follow the architecture, we'll have to deduct some points. As long as you follow the architecture, you should be fine. Okay? Does that make sense? Not a problem. All right, so if we don't have any other questions, thank you all for being here. And we won't have a class on Monday, as you know, it's Easter Monday. So our next class, next and final class, is going to take place next Thursday, okay? And let me know today if you have any questions. We have office hours from 2 to 4, so I'll be there on Slack, and if we need on Zoom as well, okay? Thank you all very much. Have a nice long weekend, and I'll see you all next week.